So chapter 5 was all about probability distributions, and so was chapter 6. In chapter 5, though, the questions were always about discrete types of data. You could say, what's the probability of getting 6 heads out of 10? But you couldn't say, what's the probability of getting 6.72 heads out of 10 flips of a coin? That made the distributions in chapter 5 discrete. In chapter 6, we're moving on to continuous probability distributions, and particularly the normal distribution. We've already talked about what it looks like to be normally distributed as far as data goes. And as far as probabilities go, it's the same idea. So to be normally distributed, data has to start low and then have high in the middle and then go low again, symmetric. The probabilities are normally distributed if they follow that same pattern, but it looks more like this blue line here, like the bell curve or the normal distribution. And it's worth pointing out some of the features of the normal distribution. The mean and the standard deviation become important for us here. And all of these pictures here, the mean is right in the middle since it's symmetric, right? So the average or the mean is right in the middle. And then, like always, the standard deviation tells you how far things are spread out. So in these pictures here, this +1 is 1 standard deviation, and +2 would be 2 standard deviations, and so on. And we already have the rule of thumb that says, hey, basically, almost all the data is going to fall within 2 standard deviations of the mean. And you can see that here, particularly in normal distributions, 95% of the data falls within 2 standard deviations of the mean. And if you go out to 3 standard deviations in either direction, you get 99.7% of the data. But really what we're going to look at is figuring out the probability that certain values fall within certain measurements, just like we did in chapter 5. So let's take a look at an example. So let me take one of our old classic examples of normally distributed data. It turns out that IQ scores, at least on this Wechsler IQ test that they use so often, are normally distributed. So that's the only requirement for using the normal distribution, by the way, is they have to tell you that they're normally distributed. There's not these 4 requirements we have to check like we had for the binomial and for the Poisson. So they'll say, hey, this particular thing is normally distributed. And they'll have to tell you the mean. And they'll have to tell you the standard deviation. So knowing that much, I could draw a little picture. I could say, hey, I know IQ scores are normally distributed, so let's draw ourselves a normal curve. Normal curves look about like that. I know the mean's right at the middle, so 100 is right there. And I know 2 standard deviations up and 2 standard deviations down will cover almost all of it. So there's like 2 standard deviations up, and there's 2 standard deviations down. Standard deviation is 15, so this would be 115, this would be 130, this would be 15 down, it would be 85, and 15 more down would be 70. So I'd say, hey, I know that almost all IQ scores fall between 70 and 130, right? So that's the vast bulk of people fall in that span. But the question they'll often ask will be something like, let's get back to blue. The question will often be something like, what % of people have IQ scores, maybe something like less than 105. So I'm going to recommend when you get a question like this that you draw a picture every single time. The picture is so important to the normal curve. So let's draw ourselves a picture. So there's my normal curve. I'm at least going to label the mean. It's not as important to label the two standard deviations on either side. You can if you want to. But really the important part here is to say I'm interested in 105. So 105 is probably about right there. I'll just label it up there, 105. Less than 105. So I'm interested in everything that's to the left of 105. I'm basically saying what percentage of the curve is there that I just shaded in yellow. Just graphically, it looks like a little more than half the curve. So I'm guessing like 55%, maybe 60%. It's a little hard to tell, but a little more than half is basically what we're getting to. And it's about time to grab StatDisk and crunch some numbers, but StatDisk only wants z-scores. It doesn't want IQ scores, because it's like you might be doing IQ this time, but next time maybe you're doing heights of U.S. adult males, and the time after that maybe you're doing the length of people's big toes, right? There's lots of things that are normally distributed, but we can put them all in the same scale by using z-scores. So in case you don't remember a z-score, way back from chapter 2 or 3, because it was chapter 3, the z-score is your data point minus the mean divided by the standard deviation. So the z-score of 105, actually let's do it down here. A z-score of 105, so that's a z-score of 105 minus 100 divided by 15. So that's a z-score, let's see, works out to 5 over 15. Works out to 1/3, or 0.3333. So 1/3, approximately 0.333. Okay, so as far as z-scores go, this is an IQ score of 105, or z-score of 1/3. Okay, now we're ready to get StatDisk up. So let's go to StatDisk, and let's go into analysis and go to probability distributions. And you will notice the very first one, pride of place, is the normal distribution. So pick the normal distribution. It doesn't give you much to put in. It just says, what's the z-value? And our z-value was 0.3333. And what it tells you, particularly the thing that we're interested in, is notice this one right here, this cumulative probability. The area to the left is 0.631, rounded to 3 sig figs. So 0.631 is this area right here. 0.631. So what percent of people have IQ scores less than 105? About 63% of them do. And I'll just put the same decimal rounding in there, 0.631. Okay, let's take a look at one more question, and then we'll look at a couple of homework examples in the next video. So let's see if we can do one more. And let's say we've got something that's normally distributed. Let's say this is the number of calories that I eat during a day. So let's say that's normally distributed with a mean of 2,300 and a standard deviation of 250. And again, just with that much information, I can make a basic sketch of how my calories are distributed. So I have an average of 2,300, some days more, some days less. And pretty much all the days should be anywhere from 500 up to 500 down, right? 2 standard deviations in either direction. So this time, let's ask the question, what percent of the time will the calorie consumption be between 2,000 and 2,500. Okay, so let's draw a picture for that and then see if we can answer it. So picture-wise, well, here, I'll just work off my same picture I have up here. 2,500 is a little bit to the right of 2,300, so it's probably, just put 2,500 right there. 2,000's a little bit further down on the other side, so maybe 2,000's over there. And I want to talk about that. What percentage of the curve did I just shade? That will match the percent of the time that my calorie consumption will be between 2,000 and 2,500. I definitely need to convert both those numbers into z-scores first. So let's get 2,500 as a z-score. So that would be 2,500 minus 2,300 over 250. So that's, let's see, that's 200 over 250, which works out to 4/5 or 0.8 as a z-score. Do the same thing for 2,000. 2,000 minus 2,300. And we still need to subtract in that order. Divided by 250. So that's going to be negative 300 over 250. Which works out to negative 6/5 or negative 1.2. So we've got these as calorie counts, but as z-scores, we're talking a z-score of 0.8 and a z-score of negative 1.2. Okay, so let's go back to StatDisk. And let's focus on this z-score of 0.8 first. So let's put a 0.8 in for a z-score. And it tells me the cumulative area to the left is 0.78814. So what we just figured out right there by doing that oops, there's 2,300. I just figured out the cumulative area to the left of 2,500 all the way down to the end. So I just worked out that was 0.788. Which wasn't really what I want, right? I want this area up here. So I actually need to chop off the part that's to the left of 2,000. So as a separate computation, I know it's a little bit clunky, but it's the way our technology is set up. Oops, there's 2,300. As a separate computation, I'm going to figure out this area to the left of 2,000. And that will then be what I need to subtract off of 788. So let's figure out that area to the left of 2,000. Figure out that area to the left of 2,000. And we'll do that with StatDisk as well. So that 2,000 was a z-score of negative 1.2. So let's put a negative 1.2 in. And the cumulative area to the left is 0.115. Just round to the same amount. Oops, that's that much right there. So to get this right up here, the area that we actually wanted, we're going to have to do the 788 and then subtract off this little bit right here by subtracting 0.115. So the ultimate answer to the question here is 0.788 minus 0.115, which is 0.673. Okay, we'll look at a couple more examples in the next video.